There are two families of hashing algorithms commonly used in digital forensics. The first is message digest, known as MD. The algorithms in the MD family are MD2, MD4, and MD5. Of these, only MD5 is used in digital forensics. MD5 produces 128-bit hash values known as message digest, but most people just call them hashes or hash sums. MD5 is an internet standard, the oldest hashing algorithm used in modern digital forensics, and is available for use license-free. The second family used in digital forensics is the secure hash algorithm, pronounced either SHA or SHA. SHA consists of a collection of hashing algorithms that produce hash values of different sizes. Remember my talk about hash sizes and collisions? Of the SHA algorithms, SHA-1 and SHA-256 are used in digital forensics. SHA-1 produces hash values 160 bits in length, and SHA's 256 hash values are 256 bits in length, which are both longer than the message digest produced by MD5. SHA-1 is also freely usable internet standard. SHA-256 was created and patented in a standard by the U.S. government in the FIPS 180-4 federal publication and released under royalty-free license. So what do all these different hash values look like when compared to each other? Yeah, they look like long hexadecimal numbers, sure, but with a little practice you can eyeball what hash value belongs to which algorithm. In this table, we see the string Pluralsight hashed by the hashing algorithms you are most likely to come across. Notice how the lengths of the hash values differ considerably. If you ever run across a long integer and you are not sure what type of hash value it is, or even if it is a hash value, the hash identifier tool in Kali Linux will help you determine what hashing algorithm you may have generated it. I've included a very short demo clip of hash identifier in this module for you to see. All hashing tools are capable of calculating a single hash value for an entire file. A problem with the single hash value method is that although you can tell that the file has changed, the hash will not tell you where in the file the change or changes occurred. One solution for this problem provided by some hashing tools is to divide the file into equal areas called blocks and calculate a separate hash value for each block in the entire file. By recalculating the hash values and comparing them to the file's previous block hash values, we can see what blocks have changed to get an idea of where in the file the change or changes took place. The smaller the blocks, the more precision we gain for locating the exact location of the changes within the file. But we also end up calculating hundreds or thousands of hash values for the file just to find changes that we may not care about. An alternative to block hashing is selective area hashing. If you are only concerned about detecting changes in specific areas of a file, you can calculate the hash values of these important areas using their byte offset values. It is often useful to create hash values for only specific areas of a file that you expect to change, such as the file's header or footer. This can be important for determining if a critical section of the file has been modified, new information has been appended or prepended to the file, or just a timestamp in the file's header has been updated. Not all hashing tools support selective area file hashing, but one hashing tool, including Kali, does.